Hello and welcome to this video. In this video, we will learn more about Python standard library. Instead of typing the problems, I have just opened the documentation from docs.python.org and we will straight up jump into library reference. So we have covered all the built-in functions. So we hop on to built-in constants and we will proceed from here. So it is built-in constants. The base built-in constants are these. The one is false, one of the constants, which is the false value of the bool type, which we use for truth testing. Now assignments to false are illegal. You can't assign to false. It's a constant and will raise a syntax error. The counterpart of false is true. So it is true value of the bool type and assignments are illegal and will raise a syntax error. Then corresponding to the null of C or none of Rust, we have a none. So it is a value which represents the absence of a value. Okay. And assignments to none are illegal and will raise syntax error. None is the sole instance of none type. So its type is also different. The type is none type. Next constant is not implemented. Now it says a special value which should be returned by the special binary special methods eq, lt, add, rsub, etc. So when you overload the operators, you can return a not implemented constant. For example, let's do one exercise for this. So I say class A, okay, and I define a function, say for equality, okay. It will take self and I say return not implemented, and then I say a is equal to a and b is equal to a. I say print a is equal to b. So let's see what it gives us. I'm not sure, I have not made this, I just made this right now. Python lib 12. Okay, a dot eq b okay. I made a mistake. So if you read this previous error carefully, it takes one positional argument but two were given. So here it is, we will have to take another argument. Oh, okay, and it says false. Okay, it seems it has implemented the equality on its own. So we say less than. So it says type error not implemented between instances of A and A. What if we say for 6? See, now it is returning 6 less than equal to. So we say not implemented. So when it is not implemented, it says it is not supported. I think that's what the message is, not implemented. So when not implemented is returned, it will say that it is not supported between instances of A and less than A and B. So this is the feature which you can use to indicate that it is not implemented. So less than was also working. That means less than was also working. Okay, less than not supported. So now the question is why this is not working. Q. This should also work. Okay, probably simply returns false. Okay, in any case, we move on. Ellipsis. The same as ellipsis, literal, triple dot. Special values used mostly in conjunction with extended slicing syntax for user-defined container types. Okay. And then we have debug, which is not important. Constants added by site modules. These are useful for interactive interpretation and should not be used in programs. So we'll skip this because most of our code will be in the files, not in interactive shell. Now we come to truth value testing. So truth value testing is done mostly inside if or while, or in our complex logic gates if you want to extract the truth value. So by default, an object is considered true unless its class defines either a bool method that returns false or a len method that returns 0. So a class object, if it has a bool method or len method which returns false or length returns 0, the value is considered to be true when called with the object. So for example, if you see 1, so you will see basic customization in library reference. So you can go and read that. The constants defined to be false are none and false. 0 of any numeric type, 0 in integer, 0.0 in float, 0j in complex number, decimal 0 or fraction 0 by 1. Empty sequences and collections. So empty strings, empty tuple, empty list, empty dictionary, empty set, empty range, all these will be equal to false. Operations and built-in functions that have a boolean result always return 0 or false or for false and 1 or true for true unless otherwise stated. Important exception. The boolean operations or and always return one of their operands. So what does it mean by always return one of their operands? We will see just now. So given below are boolean operations. So if we say x or y, if x is true, then x else y. X and y, if x is false, then x else y. Not x, if x is false, then true else false. So you see the or and will return true, not true or false, but rather x. For example, let's say x is equal to 4 or 5 and y is equal to 6. If you want to print x or y, then it should print 5 according to documentation, which it will, I guess. It will not print a boolean value of true, even though the entire expression evaluates to true. So it prints 5. Let's comment this out. So it prints 5. Now, if we say not, then it will return either true or false. So if we say not x, then it should return false. Now suppose let's consider this object A. Okay, so if we want to print A, A or A, no, this one too. We'll have to use something else, not or. Okay, so can we convert this into bool A? So it returns true. Okay, so it will return 1 or true or 0 or false. All right, so these are the exceptions, or and. Now remember that or and in almost any programming language, they are short circuit evaluations. For example, if you are testing for or and x is true, then it will not evaluate y at all. And in case of and, if x is false, then it will not evaluate y at all. Okay. About not, the third point is not has a lower priority than non-boolean operators. So not a is equal to b is interpreted as not a equal to b in parentheses, and not is equal to a is equal to not b is a syntax error. That is because of the priority of the not operator. Now we come at comparisons. There are 8 comparisons in Python. They all have same priority, which is higher than that of boolean operations. Comparisons can be changed arbitrarily. For example, x less than y less than equal to z is equivalent to x less than y and y less than equal to z, except that y is evaluated only once. But in both cases, z is not evaluated at all when x less than y is found to be false, because and is short circuit evaluation. So the 8 operations are less than, which is strictly less than, that is equality won't matter. less than equal to, which is less than or equal to, greater than equal to, equality, inequality, is means object identity, that is the objects are identical. There it probably means the id function should return the same value. Negated object identity is not. Objects of different types except different numeric types never compare equal. Okay, so if an object is of class A, another is of class B, they will never compare equal unless they are of numeric types. Numeric types means integer, float, and complex numbers. The is equal to operator is always defined, but for some object type, for example, class objects. So is equal to operator, that is EQ, is has to be defined, is equivalent to is. The less than equal to, greater than equal to operators are only defined where they make sense. For example, there is a type error exception when one of the arguments is a complex number. So non-complex numbers, you can't compare less than or greater than because there are two parts. So you have to specifically overload the operators less than, greater than, less than equal to, greater than equal to. Non-identical instances of class normally compare as non-equal unless the class defines an equal methods. Okay. So non-equal instances means the one which we have defined A and B for class A, they compare non-equal. Okay. So it is false. So for example, let's see this. Okay. Let's comment this out and uncomment this and comment this. What if we return here true? Okay, what happens then? So it started returning true. So if we implement equality, we can compare the non-equal, non-identical instances as well. Instances of a class cannot be ordered with respect to other instances of a class or some other type of objects unless the class defines enough of the method less than equal, greater than equal. In general, less than equal are sufficient if you want the conventional meanings of the comparison operations. So if we implement less than inequality, we can generally make sure that classes can be ordered. For example, possibly you can see this behavior when we invoke sorted on a list of classes. The behavior of the is and is not operators cannot be customized. Also, they can be applied to any two objects and never raise an exception. So for example, if we print A is B, then it will return false. Now, two more operations with the same syntactic priority in and not in are supported by types that are iterable or implements the contains method. Like when we say for I in range x comma y, or when we say for a in some iterable like a list or a string. In that case, in and not in are tested. Or for example, a set. The set will probably implement contains method, so that existence of an element in set can be tested. Now we come to numeric types. So as I said, there are three different numeric types: integers, floating point numbers, and complex numbers. In addition, booleans are a subtype of integers because false is 0 and true is 1. Integers have unlimited precision. The number of digits by default is set to 4,300 digits. Floating point numbers are usually implemented using double INC, that is IEEE 754. That is the specification. So if you want to read about floating point numbers, you can read this article on Wikipedia, and not this article on Wikipedia will tell you all the details of IEEE 754. If you're interested in knowing how floating point number works, you can go through this. So information about the precision and internal representation of floating point numbers for the machine on which your programming is running is available in sys.floatinfo. Complex numbers have a real and imaginary part which are a floating point number, as we have studied earlier also. To extract these parts from a complex number z, use z.real and z.imaginary. The standard library includes the additional numeric types fractions.fraction for rationals and decimal.decimal for floating point numbers with the user definable precision. So if you want a higher or lower precision, you should use decimal.decimal or fractions.fraction. Numbers are created by numeric literals or as the result of built-in functions and operators. Unadorned integer literals including hex, octals, and binary numbers yield integers. Numerical literals containing a decimal point or an exponent sign yield a floating point number. Appending j or small j or capital J to a numeric literal yields an imaginary number, a complex number with zero real part, which you can add to an integer or float to get a complex with real and imaginary part. Python fully supports mixed arithmetic. When a binary arithmetic operator has operands of different numeric types, the operand with the narrower type is widened to that of the other. For example, if you divide an integer with a float, then integer will be widened to match that of float, and the result will be a float. For example, when you add an integer and a float, the result will be a float. And if you add an integer with a complex number or an imaginary number, the result will be a complex number, because complex number is of wider type than integer or float types. Where integer is narrower than floating point, which is narrower than complex. That's what I said. A comparison between numbers of different types behave as though the exact value of those numbers were being compared. So if you see this 2, so as a consequence, the list 1, 2 is considered equal to 1.0 and 2.0, and similarly for tuples. All numeric types except complex support the following operations. So except complex, that is integer and floats, you can add, you can subtract, multiply, divide, get float quotient, remainder, negate them, keep them unchanged, get absolute value, convert them to integer, convert them to float, create complex numbers out of them, find conjugates from complex numbers, or for real numbers and floating point also you can find conjugate. You can get div mod operator, so it will give you the float division and the remainder. You can compute the power and you can use the power operator. So these are the operations we can invoke on any numeric type, except complex numbers, that is on integer and float. Now these are the notes. So if you look at the note number 1, that is the float quotient, that is note number 1 and 2, and for remainder also. So note number 1 says that also referred to as integer division for operands of type int, the result has type int. For operands of type float, the result has type float. In general, the result is a whole integer, though the result's type is not necessarily int. The result is always rounded towards minus infinity. This is an important point to remember, that when you divide, the result is rounded towards minus infinity. So 1 divided by 2, that is the float quotient, is 0. Minus 1 float quotient is minus 1. 1 float quotient minus 2 is minus 1, and so on. Point number 2 says that not for complex numbers. Instead, convert to floats using absolute if appropriate. So this is about point number 2. Okay. Point number 2. Now point number 3 is about converting x to integer. So 3 says that conversion from float to int truncates, discarding the fractional part. See math.floor and math.ceil for alternative conversions. So math.floor will get the integer part and ceil will get the next integer. Point number 4 is for converting to floating points. Float also accepts the string nan and inf when with an optional prefix plus or minus for not a number and positive or negative infinity. Now next are power. Python defines power 0, 0 to power 0 is to be 1, as is common in programming languages. The numerical literals accepted including digits 0 to 9 or any Unicode equivalent. So point number 6 is for which one? For complex and floating point and int. So numerical literals accepted include the digits 0 to 9 or Unicode equivalent. And ND property, code points with the ND property. I don't know what is ND property, so we will have to see. Numeric type text. So these are the numeric type text. So for example, this is vulgar fraction of 1/4, vulgar fraction 3/4. So BC, BD, B. So for example, I am tempted to test this. Okay, but maybe in the next video I'll test this. Okay, I promise that I'll test this these numeric texts. It is quite tempting to test something which is not there, which are not studied. I have not studied the entire standard library in detail. That's a confession I'll make here. All numbers dot real types int and float it also include the following operation: math dot trunc x truncated to integral, round x comma n, x rounded to n digits, rounding half to even. If n is not omitted, it's default to 0. So we have seen the round function. Maths dot float, the greatest integral less than equal to x. Maths dot ceil, the least integral greater than equal to x. For additional numeric information, see math and see math modules. Now we come to bitwise operations on integer types because they only make sense for integers. The result of bitwise operations is calculated as though carried out in 2's complement with an infinite number of sign bits. The priority of binary bitwise operations are all lower than numeric operations and higher than the comparison. The unary operation tilde has the same priority as the other numeric operations. So for example, if you are not aware of what 2's complement is, you can hit my website. You go to C programming and you go to 2's complement and 1's complement. Then you can study. It's not in a lot of detail, but there is a little bit information there. So on number system and all, you can study here, or you can simply Google 2's complement. And Wikipedia will have an article on it. Yeah, you can go and read here 2's complement. This is what almost all the computers implement. Most computers implement this, except few esoteric ones work in 1's complement. So the Boolean operations are x or y. So this is bitwise OR of x and y. So if either of x or y is non-zero, then it will be true. Bitwise exclusive OR of y. So truth table, I think if you want truth table and all, so again you can go to my website and you go to C programming and bitwise operations. So the truth tables are given here for different gates, and others you can construct based on these gates. I have also given XOR, NAND gate and NOR gate truth tables. NOR gate truth table I have not given, or I have given. I think I have given. So the labels are below that. So this is NOR gate, this is NAND gate, and so on. I should have seen this. I didn't observe it. Okay. So this is and, this is less than, left shift, right shift, and tilde. So bits are inverted. So I think I'll stop here. In the next video, we will see additional methods on integer types and we proceed from there. So we'll continue this till we cover the entire standard library. I will cover most of it in the series. So stay tuned for the next video, and I hope that you have found my reading useful and informative, and plus the extra bits which I add in terms of programs. So make sure you smash that like button, share the video as much as you can on social media so that your friends and family can benefit from this, and otherwise increase the reach of video. Make use of the comment box to interact with me. Some of you might be veteran programmers or may have many years of experience in maybe other programming languages. So it would be nice if you can exchange ideas, and your actions like subscription, sharing and liking actually increases the reach of the video. So I'll much appreciate if you perform these actions. Thanks a lot for watching. Happy programming.